Hi there, Mr. Sutton here. I've got the Pre-Cal Honors 8-4 Part 1 homework solutions on conversion and convergence power series. On this problem, we're trying to find the interval of convergence and function of x represented by this geometric series. So let's start by getting the a1 and the r values. For a1, the first term, we just plug in 0, the lower limit of summation, for n. 3 times something to the 0 is just going to be 3, so that's our a1 value. For r, we have the thing that's being multiplied by itself over and over again. That's this x minus 1 to the n piece, or x minus 1 over 2 rather. The exponent doesn't come with it, just the thing that's being multiplied. Now let's do interval of convergence first. So that's just going to be taking the r value, the absolute value of that, and setting that less than 1. And now we can rewrite this as negative 1 less than x minus 1 over 2 less than 1. You also could have multiplied by 2 right away, but we could do the 2 down here as well. So multiplying everything by 2, that'll be negative 2 less than x minus 1 less than 2. And then adding 1 to all three sides here, we've got negative 1 less than x less than 3. So that's our interval of convergence for this series and the function. Next, to write the function itself, we're going to use a1 over 1 minus r, the general formula for the sum. So in this case, we've got 3, the a1 value, over 1 minus all this craziness here. And if we want to simplify this a little bit, we can use a common denominator of 2. So 2 minus x plus 1 if we distribute that negative. And then, let's see here, we've got 1 plus 2 is 3, so we've got 3 minus x over 2. And then if we same change flip that thing, multiply by the reciprocal, we've got 3 times 2, or 6, over 3 minus x. For this problem, we want interval of convergence and function of x represented by this geometric series. Let's start by getting the a1 and the r values. For a1, we're just going to plug the lower limit of summation, which is 0 in this particular case, in for n. So we've basically got something to the 0 times something else to the 0, or 1 times 1. So that's just an a1 value of 1. Now for the r value, we're just looking for the thing that's being multiplied by itself over and over again. So that's going to be the negative 1/2 and this x minus 3. Both of those together comprise the r value on this. To get the interval of convergence, we're going to take r, take the absolute value of this, and set it less than 1. Now a little trick you can do when you put this between negative 1 and positive 1, since this is all in an absolute value and all of the stuff in here is being multiplied by this negative, you can actually ditch this negative when you take this out of the absolute value, and it'll come out to the same thing. So now let's just solve for x. We can multiply everything by 2, so that'll be negative 2 less than x minus 3 less than 2. And then adding 3 on all three sides here, we've got 1 less than x less than 5. Now let's move on to writing the function itself. So we're basically going to do a1 over 1 minus this r value. So 1 over, 1 plus 1/2 x minus 3. And we can clean this up a little bit here. This is really 1 plus x minus 3 over 2. We can make this 2 over 2 to combine it with that fraction. So this will be 2 plus x minus 3, all of that over 2 in that denominator. And now we can rewrite this as, let's see, this is actually x minus 1 over 2. And we can multiply by the reciprocal and bring this 2 up here. So when the dust settles, then we're going to end up with 2 over x minus 1. For this problem, we're trying to find interval of convergence and a function of x represented by this geometric series. So let's begin by finding the a1 value and the r value, since this is an infinite geometric series. So for a1, if you plug in 0 for n, because that's your lower limit of summation, we've got 2 to the 0, x to the 0. That all just comes out to 1. For the r value, that's going to be whatever is being multiplied by itself over and over again. Since 2 and x are both being raised to the n, 2x, that whole thing, is our common ratio. Now for the interval of convergence, we're just going to take our ratio, the absolute value of 2x then, and make that less than 1. So we can rewrite this as negative 1 less than 2x less than 1. And if I divide everything by 2, I've got negative 1/2 less than x less than 1/2. So there's our interval of convergence. For the function of x, we're just going to plug the a1 and the r into our infinite sum formula. That's a1 over 1 minus r. So we're going to write f of x equals 1 over 1 minus 2x, and that's it. On this problem, we're trying to find interval of convergence in the function of x represented by this infinite geometric series. So for this one, we're going to start by getting the a1 value. So that's going to be whatever you have when you plug the lower limit of summation, which is 0 in this case, in for all the n's. So we've got something to the 0 times something else to the 0. All that's going to come out to 1. For the common ratio, the r value, that's whatever we're multiplying by itself over and over again. So since we have -1 and x plus 1 both raised to the n, that means that negative parentheses x plus 1, this whole thing here is our common ratio. This is what we're multiplying by over and over again. All right, to get the interval of convergence, we're going to take the absolute value of our r value, so absolute value of negative parentheses x plus 1, and set that less than 1. And with absolute value, a little trick, if you have a negative being multiplied by everything inside the absolute value, you can just drop that negative. So we can rewrite this as -1 less than, now positive x plus 1 less than 1. So again, we just drop this negative in here because we have an absolute value, and this negative applies to everything inside. All right, so now we're just going to get x by itself by subtracting 1 from all three sides. So we have -2 less than x less than 0. And there's our interval of convergence. Now to get the function of x, we just have to plug the a1 and the r into the infinite sum formula. So that's a1 over 1 minus r. So 1 over 1 minus negative x plus 1, or 1 plus x plus 1. And then if you want to simplify the denominator, we can call this 1 over x plus 2. On this problem, we want to know the interval of convergence for this infinite series. Now to make my life a little bit easier, since the numerator and denominator are both all being raised to the n power, I'm just going to write this as one big fraction, x plus 2 over 2, all of that raised to a single power of n. A little bit easier to look at. Okay, so the key on this one is recognizing that we have a geometric series. There's something that just keeps getting multiplied by itself over and over again as represented by this exponential function in here. So because this is geometric, I'm going to just use my r value for a geometric series and let the absolute value of that be less than 1. And I'll just work from there to get one of these answers. So my r value is x plus 2 over 2. It's just the thing that we're multiplying by over and over again. So I'm going to write absolute value of x plus 2 over 2, all of that, is less than 1. And now I'm just going to turn this into normal inequality notation with no absolute value and solve for x. So I can rewrite this as -1 less than all this stuff, less than 1. And that means, well, I'm just going to isolate x, so I'm going to have multiply everything by 2 to start with. So I've got -2 less than x plus 2 less than 2. Next, I'm going to subtract the 2 in here from everything. So that's -4 less than x less than 0. And let's just match that with one of the answer choices. A and B are pretty close, but notice that A has strictly less than instead of less than or equals, so A is the answer that we want here. For this problem, we have kind of an oddball situation. They want us to solve for x, and x is wrapped up in some kind of infinite series. The key on this problem is recognizing this is a geometric series, an infinite one. So our goal on this one is actually going to be to rewrite this as a function using our infinite sum formula, and then set that equal to 20 and solve for x. So let's start by getting the a1 and the r value. That's what we need to rewrite a series as a function. So a1, that's going to be what you get when you plug your lower limit of summation, which is 0 in this case, in for n. X to the 0 is just 1, so that's our a1 value. For r, it's whatever is being multiplied by itself over and over again, so that's x in this case. So we can write our function then as 1 over 1 minus the ratio of x. And before we go ahead and actually set this equal to 20 and solve, let's get the interval of convergence for this, just to know what x values will actually be good for answers. So if you take the absolute value of x and put that less than 1, we can write -1 less than x less than 1. We know that this is only true if x is between these values. So if we set this equal to 20 and get a number that is not between -1 and 1, we know that they just gave us a problem that couldn't be solved. All right, so let's hope for the best and set this equal to 20. Multiplying by x minus, or 1 minus x, I've got 20 minus 20x equals 1. And then if I subtract 20, that's negative 19. Divide by negative 20, we have x equals 19 twentieths. 19 twentieths is between negative 1 and 1. So that means that this is a good answer. It actually falls in the interval of convergence, and we've solved the problem. For this problem, we want to know what are all values of x for which this series converges. The key on this one is recognizing that this is a geometric series. We have something being multiplied by itself over and over again. So with a geometric series, we just have to figure out the r value, the common ratio, and see what values of x make that less than 1 inside an absolute value. So I'm going to get my r value. That's going to be the thing that's being multiplied by itself over and over again. 2 over x squared plus 1. There's my r value. Now I need the absolute value of this to be less than 1. Basically just using our infinite geometric series rule. And this is where it gets a little bit tricky. We know from the answer choices that I have a negative 1 or a positive 1 involved somehow in this process. But solving this with absolute value is kind of a nightmare. So let's go through it step by step. First thing I'm going to do, and I can do this without removing the absolute value, is I'm going to divide both sides by 2 just to get rid of that. So I'm going to have 1/2 on the right side, and I'm going to have just absolute value of 1 over x squared plus 1 on the left side. Inequality symbol does not change directions at all. Here's where it gets a little bit interesting. Logically thinking about this, in order for this fraction to be less than this fraction, that means the denominator over here has to be bigger than the denominator over here. Bigger denominator means smaller overall fraction. So that means that this x squared plus 1 stuff has got to be greater than 2. In order for this fraction to be smaller than this fraction, the stuff down there has to be bigger than the stuff down here in the other fraction. All right, so where do we go from here? Well, we can subtract 1 from both sides. Nothing fancy going on there. But now we have x squared greater than 1, and how do we solve this? You might remember solving inequalities, quadratic inequalities. If not, the basic idea is you move the 1 over here, factor, zero it out, figure out the zeros, and then do sign analysis to see where everything comes out positive. Another way of doing this is just reasoning it out. If I'm squaring a number and it's bigger than 1, what kind of number must I have been squaring? Well, if I square something bigger than positive 1, I get something bigger than 1. Also, if I square something less than negative 1, I'm going to get something bigger than 1. Like if this were a negative 3 for x, squaring that would actually give me a positive number bigger than 1. So that means that x has to either be less than negative 1 or x has to be greater than positive 1. And out of all these answer choices, the only one that fits this description is choice D.